Hello everyone, welcome to the channel Upgraded than Yesterday. Today we are going to learn about Java Memory Model. Overview of Java Memory Model. When you write a Java program, the code execution involves a variety of components in memory. The Java Memory Model is a specification that defines how Java threads interact with memory, including how variables are stored, read, and updated, and how changes made by one thread become visible to others. It ensures three key guarantees. Visibility. When one thread updates a variable, other threads should see the updated value. Ordering. Instructions execute in a predictable order. Atomicity. Any operation executes completely or not at all. Look at the diagram. The Java memory model consists of 5 components, that is method area, heap area, stack area, PC registers, and native method stacks. Each of these components are serving a specific role in program execution. We are going to explore each of these components in detail, so stay with me. Method area or meta space. Method area is created on JVM startup. Prior to Java 8, it was logically part of heap area, but with the Java 8 release, it was implemented as meta space and moved to native memory, which is outside of heap area. The memory in the method area is allocated when the JVM loads a class. Method area stores only the class level information required during a program execution and can't store objects. This class level information includes class metadata. Class metadata is the information about the classes, interfaces, and methods. Static variables. Static variables means class level variables that can be accessed by any class. Constant pool. The constant pool stores constants such as string literals and object references. Since the method area stores class level information, which is common for all the threads, so the method area is shared across all the threads. The garbage collector may run on method area to free up the spaces, though this depends on the internal implementation of JVM. Garbage collectors like G1GC or ZGC supports class unloading from meta space. Meta space throws out of memory error when it cannot allocate space for a new class which is ready to load. Look at the diagram. There is a class test and has a static variable count assigned a value 10. In meta space, the following information will get stored. Class metadata. Class name will be test. Superclass name object, as every class in Java is a child class of the object class. Interface. None, as the test class does not implement any interface. Access. Package private or default, as no access modifier is explicitly defined. Static variable information. Variable name is count, type is integer, value is 10. Additionally, the bytecode information for the static variable is also stored in meta space. Heap area. Heap area is the largest memory area in JVM and is created on JVM startup. Heap area used to store objects, instance variables, and arrays during runtime. Since heap area stores objects that are shared across the program, so the heap area is shared across all the threads. The size of the heap is not strictly fixed. The JVM uses two parameters to define its size: -xms for initial size and -xms for maximum size. The garbage collector runs on the heap area and checks for objects that are eligible for removal so that it can free up some space. However, if no objects are eligible for removal and if new objects are continued to be added, the heap will eventually reach its maximum size limit, and throw an out of memory error. The heap is divided into two parts, young generation and old generation. When an object is created, it lives in young generation area. It consists of two areas, hidden space and survivor space. When an object is created, it is allocated in hidden space. But any object that has survived at least one minor GC run, that object lives in survivor space. During a minor GC run, objects still in use are moved from hidden space to the one of the survivor space S0 or S1. Objects that survive in hidden space and have already spent time in one of the survivor space, say S0, then that object is moved to the other survivor space S1. Active objects are continuously moved between S0 and S1 to delay their promotion to the old generation, allowing the JVM to manage memory more efficiently. Old generation. The old generation stores long-lived objects that have survived multiple rounds of GC runs. Objects such as singletons, cached data tend to live longer and therefore resides in the old generation. PalmGen or permanent generation. PalmGen was part of JVM until Java 7 and was decommissioned in Java 8. It stores class level information similar to what Metaspace stores today and was part of heap area. Since PalmGen was fixed in size, it frequently threw out of memory error. This limitation was the primary reason why it was replaced by Metaspace. Look at the diagram. There is a student class with field ID and name. When a student object is created, the object itself allocated in the heap area, while the reference variable is stored in the stack area. The stack holds the reference variable along with the memory address of the student object present in the heap area. Stack area. The stack area is a part of JVM memory used to store method execution data such as local variables, method calls, and object references. Unlike the heap, the stack area is not created on JVM startup. Instead, a new stack is created whenever a new thread is created. By default, one stack area is created for the main thread and each subsequent thread gets its own dedicated stack. The stack is not shared across all the threads. Every thread has its own stack. If the stack were shared across multiple threads, multithreading would become a nightmare, as threads could override each other's data, leading to incorrect and unpredictable results. The stack is fixed in size and stores temporary data, and that data is removed from the stack once the execution of the method is complete. Execution within the stack follows last in first order. A stack overflow occurs when there is infinite recursion or too many nested method calls. Look at the diagram. There is a class test with a main method. Inside the main method, a new thread is created using a lambda expression to implement the runnable interface, with the run method containing a local variable x is equal to 10. In this case, there are two threads created, the main thread and the new thread. The JVM will create a separate stack for each of these threads. In the main thread stack, the following informations are stored: the local variable args of type string array, the thread object reference, and the return statement information. In the new thread stack, the following informations are stored: the local variable x is equal to 10, the runnable object reference, and the return statement information. The heap area, which is shared between both the threads holds two objects, the thread object and anonymous object that implement the runnable interface created via lambda expression. Program counter register or PC register. The PC register is a small memory area in JVM that stores the address of the current instruction being executed by a thread. Each thread has its own PC register and it is thread specific and not a shared memory. PC register stores only the address of the instruction and not any data. In multithreading environment, the JVM rapidly switches between multiple threads, a process known as context switching. During this switching, the PC register saves the address of the last instruction executed by a thread. So, when that thread resumes execution, the JVM knows exactly where to continue from. A simple way of thinking about it is the PC register works like a bookmarking a page while reading a book so that the reader can resume the reading correctly. Look at the diagram and the animation. There is a class test with the main method containing two local variables x is equal to 10 and y is equal to 20. For this, the stack is created for the main method as shown in the diagram. When the execution of the main method begins, the PC register holds the address of the first instruction of the main method, which is 000. As execution proceeds to the next instruction, that is local variable x is equal to 10, the PC register updates to hold the address of the instruction, which is 004. Execution continues in this manner with the PC register updating to the address of each new instruction being executed, as demonstrated in the animation. Finally, once all instructions have been executed, the PC register clears the stored address. Native method stack area. The native method stack is a part of JVM memory used to support the execution of native methods. Methods written in other languages such as C or C++. It is similar to the stack area dedicated to native method execution. Java cannot directly interact with OS level operation, hardware, or low level system calls. To handle this, native methods are written in languages like C or C++ and accessed by Java through JNI, that is Java Native Interface. The execution of this native methods call takes place in the native method stack. Native method stack area stores the following: native method calls, local variables of native methods, intermediate execution data. The native method stack is not shared across all the threads. It is fixed in size and stores temporary data. Entries are removed from the stack once the execution of the native method is completed. Similar to the regular stack area, the native method stack throws a stack overflow error when there is infinite recursion or too many nested native calls. Look at the diagram. There is a class test with a main method and a native method start. Notice that the start method is declared without a body, but the native keyword is there in the declaration. This indicates that the implementation of this method has been written in another programming language such as C or C++. In this case, the JVM creates two separate stacks, one stack for the main thread to handle regular Java executions and a native method stack dedicated to the native method calls. Additionally, a heap area is created to store the test object. With that, we have covered all the components of Java memory model. Hope this gave you a clear understanding of how each component works. Thank you for staying with me.